Can I start?
Yes.
Okay. Well, thanks a lot for the invitation. It's a pleasure to be here for the last 2 days. I'm coming from ICTP. So yeah, today I would like to talk about the recent work that we put out during the summer. This work was done with Pietro Baratella, who is a postdoc at Ljubljana, and Emanuele Gendi, who's a postdoc in Munich. And like our work was planned to finish earlier because there was another interesting work that came out a couple of weeks before us, which is this one by Daniel Schubring, which there is a slight overlap in some applications that that work looks at. So I recommend also looking at that work. Anyway, so as we all know, normally when we do particle theory, we start with some action, and then we compute observables like the matrix, the spectrum, and other quantities that we may be interested. But one question that I'm going to discuss today is how do we go from S matrix to other observables like the spectrum of the theory by passing the Lagrangian formulation. All right. So some intuition about why this can be true at all is the following. So this is realized very explicitly in 2 dimensions, but we'll see that also in higher dimensions this idea can be realized, which is and some intuition behind is that if you look at some partial wave or some 2-dimensional scattering, the amplitude can look like this. So these are 2 diagrams. And instead, if you look at the right, the thermal vacuum energy looks like vacuum diagrams. So you may imagine that to go from here to here, there is some sort of trace going on the diagrams. And this, of course, and we'll see that this sort of tracing is realized precisely. Perhaps what I should say is that the fact that from microscopic physics we can derive thermodynamical quantities is not surprising. We are very used to that. Perhaps what is surprising is that the way this information is encoded is very simple, okay? And the formula that encodes this information is this one here. This equation was derived by Dashenman and Bernstein more than 50 years ago. And the plan for today's talk is that first I would like to give a review about how this equation can be at all true, okay, why this equation is true. And then we'll discuss application of this equation, okay? So, and well, pictorically, we'll see over and over that we can think of, so this is the fullest matrix of the theory with connected and disconnected matrix elements. And pictorial, so what we are doing is that we are tracing the phase of the fullest matrix and integrating this function with some Boltzmann factors. And intuitively, we can think that this tracing and these Boltzmann factors, what this building is the thermal circle that we normally think about when we think in the path intro. Okay.
So it's just the 2-to-2 S matrix, or
this is the fullest matrix, end to end.
when you say like as in 1E or lots of E?
What is E?
What is E? I mean, there are lots of kinematic variables. So what is
Yes, it's going to appear. I want to it will become clear, but it's the total energy of the state. So in end to end, you take all the energies of the n particles, and that's the energy of the state. That's the energy. That's E. It will become clear when I discuss the derivation. Okay. If you give me a second for all the questions, then let me answer. So when S is the identity, so no interacting theory, this goes to 0, and this is the free theory partition function. Okay. I will. Many questions I hope will be answered in the following 2 slides. Otherwise, you ask me again. So let me say these very basic comments on the formula before I dive into more details. First of all, very basic point is that because S is unitary, this is going to be a purely imaginary function. there's an extra factor of I, so this whole thing is explicitly real. Okay. Then it will become clear when I discuss the derivation, but let me see that this is a full S matrix. So as defined usually in textbooks like this, and we'll see that this S matrix is defined via the Riemann-Schwinger. Okay. So we usually separate between the full interacting part and some identity. Okay. And so more basic things is that normally this equation and most of the uses of this equation in the literature is either in relativistic systems, in non-relativistic systems, or is often used to argue that so people that work with hadron gases, where they have long-lived hadrons, and they want to argue that a long-lived particle contributes to the entropy as an unstable particle. This is something very intuitive, but one formal way that people like to argue is by considering some 2-2 scattering, where you change a long-lived particle, and in narrow-width approximation, it just clicks as a delta function in this formula, and it's the degree of freedom you should count. Some basic thing. So one question is, well, this formula is pretty old, so why now? Why am I interested now on this equation? And let me give you 3 quick motivations before I dive into the formal derivations. So one motivation is that, as probably many of you know, is that there's been a resurgence in the last decade or more about constraint and effective field theories using S matrix methods. This is under the name of positivity or bootstrap. And typically, these works give plots like this, where there are some parameters of the S matrix or some coefficients, and the theory should live within some convex and bounded space. And well, it's interesting that we can recast information of this type into derived thermodynamical quantities. And a motivation for hoping that this can leverage further constraints comes, for instance, there's a classic example in model building for inflation called gauge condensation, where people back in the day considered Lagrangians, which are P of x, functions of P of x, where x is the kinetic term. And so these theories satisfy a bound, which is that the function P, in order for this theory to be complete, must be convex. Okay. And this bound doesn't come from looking at 2-2 scattering, but it comes by putting the x on a background and asking for the speed of sound fluctuation in this theory to be below the speed of sound. So there are correlative phenomena that we may expect to get constraints of by looking at finite density or finite temperature. Perhaps the second motivation is the one that is most interesting to me, which is that the S matrix methods have been highly developed in the last decades, and we would like to recycle S matrix information in order to go further in the QCD equation of a state. This I'm going to review later on today in this talk. What is the status of the QCD equation of a state, and why we can do better with S matrix, with the vacuum S matrix. And well, finally, of course, the very first thing I mentioned is that in cases where we can guess the S matrix, but we don't know the action, like for instance, if we are considering effective filtration on trivial backgrounds, then this would be a way of building the thermodynamics. So that was the introduction. Let's now dive into very quickly the derivation, and then I will discuss examples that will perhaps elucidate the formula. So this is the derivation. So for most of the talk, I will keep the chemical potential to 0, but it's easy to keep it on if you want to reinstate it, okay? So the logic is the following. The partition function, thermal partition function is nothing but this. And then we can write it as a simple integral of these resolvents. So these resolvents are nothing but Dirac delta. It's a Dirac delta that clicks at the positions of the spectrum. So this is clear. And now our task will be to relate the resolvents into with the S matrix. Okay, that's the step of the second step of the derivation. Okay. So for that, I just define the resolvent, the free theory resolvent and the interacting theory resolvent. Okay. So now the steps, the proof proceeds in two steps. First, I'm going to claim that that you can write the S matrix as this product of resolvents, and this follows from some simple manipulations of the Liebman-Schwinger equation. And the second step of the proof is that via some simple algebra under the trace, the derivative of this representation of the S matrix can be brought into this equation, which is the sum of free theory resolvents and interacting theory resolvents. Okay, these both of these steps are simple algebra, and then this equation here, upon iterating by parts, we can remove the derivatives and write it as some log of the S matrix, which is a nicer way of presenting. Okay. So as it stands, this is very general for quantum systems. This way of presenting the partition function. Okay. Now, what I want to say, few more things I want to say is that instead of the partition function, what we would like to work is with some extensive quantity, and for that we're going to consider the log, okay, of the partition function and construct some free energy, okay. Now, when we take the log, as we are very accustomed to, it simply amounts to take the connected piece of this equation, okay. Here there is a subtlety, which I will elucidate in the following slides, that you should take the connected trace, which is not the same as the connected S matrix. As we saw in the previous slide, this was the full S matrix. And what we should do is, in order to extract the extensive piece, we do connectedness after trace. I'll discuss what this means in few examples, okay? So that's the main formula I'm going to be working on. And now I'm going to proceed by examples and explain what is the state of the art and what we can get out of it, okay? So the two main examples I would like to present will be QCD and so four-dimensional QCD and some simple toy models, which are integrable QFTs into dimension, okay?
Wait,
But,
so just to clarify,
yeah.
I think I understand that. F0 is the free particle free energy for all the scattering states.
F0?
Yeah, F0 is you're treating like every scattering state as a free particle, basically.
F0 means no interactions or zero count.
Yeah, but what's the set of states?
What is the states? Very good. So then I think one question related to this is also what happens with bound states, for instance. Should you put the bound states in which side of the equations? So here the way in this equation, it's very perturbative. So the set of states that I'm putting here are simply the free theory asymptotic states. So one particle, two particle, three particle states.
But you're talking about the real asymptotic. So in QCD, you're talking about free protons, not free quarks.
I understand, but in QCD, I'll be using this equation at high energy. So when above the confinement scale. Okay. So the states that I'm testing covered in QCD are going to be gluons and quarks.
But if you did it at low temperature,
If I do it at low temperatures, I'm not allowed to do that.
you're not allowed to do
No.
The
No.
equation is wrong, or
No. The equation is correct, but in the confining theory,
I thought that your formal manipulations seemed like they would be correct as long as you identified everything that you had a subscript 0 on as the in and out Hilbert spaces of the theory.
no. This is entirely correct. The question you were asking is we could fill it also for some calculation of some matrix element, right? Which are the symptotic states that we put when we do scattering at high energies. We're not going to use pions, very boosted pions. We're going to do E plus E minus to gluons or quarks, right?
Well, in practice,
In practice.
principle.
Right. No. So you're completely right. As a matter of principle, what you should be here tracing is only on the physical states of the theory. Okay. But in practice, I'm going to use it in the perturbative high energy regime, but I'm going to be using it by tracing over quarks and neutrons. I mean, it's a fair question, but I should also say that there are a number of like conceptual or subtle questions that we can ask about this equation. But I'm going to take a very practical approach, which is that for the time being, I would like to understand this equation in perturbation theory, in a perturbative regime. Okay. But let me start with the most simple case, which is the free theory, okay? Because in the free theory, we're going to already understand a number of things. And in particular, the free theory is going to teach us what on earth it means to take connectedness after the trace, okay? So this is what it means. So here you can think I'm doing some free scalar or something like that, okay? Some free boson. Okay, so this equality is pretty obvious. I'm just I'm sandwiching the exponential among free states and dividing by n factorial because they are identical particles, and otherwise I'll have redundancy on the phase space. Okay. So now connectedness, recall that it came by asking that we're looking at the log of the partition function. So connectedness at the end of the day has a meaning of extracting a single volume factor. That's the meaning of connectedness. Okay. So I'm going to connectedness because it has a geometrical interpretation. So think of the normalization of the states. It is delta function plus all the permutations. Okay. But now we are supposed to identify both states. And this in general is going to generate a crazy amount of, so you can get the delta zeros, which are volume factors, up to power n, okay? But connectedness instructs you to keep only one delta zero, okay? And the lemma is going to think like this. You have 4 particles flowing to 4 particles, and you should connect, you should identify the particles. So as I say, here, 1 goes to 4, well, this one, not very well written, sorry. 1 goes, yeah, sorry. 1 goes to 2, 2 goes to 3, 3 goes to 2, 4 goes to 1. So in this way, you can see that it's a connected loop inside in the cylinder, as opposed of connecting, say, pairwise these 2 particles and these 2 particles. So a fully connected diagram generates a single delta zero or a single volume factor. So connectedness goes in hand with the extensivity of the quantity we are computing. And okay, this is important because when we will do interactions, this same rule applies. Okay, we'll have vertices interactions, but we'll always look for diagrams that are fully connected. Okay, it have single volume factor. So well, this level computation is already nice because so out of this n factorial permutations, n minus 1 of them, n minus 1 factorial are can be fully connected. So this removes the factorial from here, and we give a single power of 1 over n. Now this sum can be done, and we recover the classic textbook result for the free theory partition function. Okay, but here it's already like a hint of something that is going on, because in this way of computing, we are only counting a physical stage of the theory. Okay, so if I'm in the high energy perturbative regime of QCD, say of Fury Mills, the 2 physical states that I should count are the 2 polarizations of the gluons and nothing else. So if I take the result here and multiply by this, you already get the free theory Fury Mills. Which you can contrast. So the calculation will proceed by computing the Gauss loop, the gluon loop, and of course you get the same number of degrees of freedom. It's usually not a big deal. Okay. Okay, so this was just to teach you what it meant connected. Okay. Now let's move on and let's add interactions in a QCD. Okay. Now apologies. Right. So now in the matrix formula, in principle, you should expand in powers of t. Okay. So a leading quarter, we should only keep 1 power of t. Okay. So this is a simple expansion of the log. Okay. And now, what I'm not going to prove here today, but you're going to look it up, is that there's a nice effect, which is that if you consider one single insertion of t of the matrix, and you allow for any number of spectator particles that do not interact, those are easy to sum over all these spectators. And somewhat unsurprisingly, they are summing to the particle densities. Okay? So there is this close formula where you need to trace over t with the particle densities, and now this t is the connected one, because you have already removed all the particles flying around that do not connect. Okay? Now there is an extension of this equation where you have multiple insertions of t and higher orders. Okay? But for now, bear with me that this equation is correct, and it's actually very intuitive. Okay? So you should trace over the T matrix, the vacuum T matrix, weighting by the particle density. Okay? So this is the number density of the proposal. Okay? All right. So now we can apply this to the Parquet-Taylor equation. So it is well known that the Parquet-Taylor equation, when you glue it in a right manner, it knows about the beta function of QCD. But here I show you that if you glue it in the right manner, it knows also about the two-loop thermal partition function, which is what this equation is going to show you now. So this is 4 gluons, all incoming here, and from here by crossing various particles, we'll get all the physical amplitudes that are there, so plus, the time reversal 1, and plus minus to plus minus. Okay. Now the nice thing is that all of these amplitudes, all these different amplitudes in the forward limit, they give the same factor, and it's some number. Okay. So it cannot get simpler, because then we are only left to integrate over particle densities times this factor here, and we need to add we need to account for the various polarization amplitudes. Okay. All right. You integrate this basic thing, and you get the two-loop thermal partition function at order is alpha s. Okay. Actually, I won't review it now, but the state of the art, like full state of the art, is only 1 order higher than this calculation. Okay. Now this calculation I just did in one piece of paper. If you go to your favorite thermal theory book, it's a bit more messy, because you need to do these optional diagrams, add them up, and if you do this calculation, of course, it matches what I just showed you. Okay. So far, this is a pure glue, but okay, it's a no-brainer to add matter. But adding matter, it shows a nice effect, which is the following. So again, all the matter amplitudes at the level in the forward limit, they give the same factor. So again, we only need to count the number of states, and well, you get this factor.
So what's it on the forward one? Oh, because we want the phase.
Where
do you want the forward one?
Forward limit. It's because of the trace, yes. We're always on the forward limit. This is going to play an important role, because I'll discuss more of this in a second. So there's a synchronized effect here, which you have imputed, which is that at T level, you have a T-channel singularity in some matrix element. So when you trace, you could be worried of hitting this forward divergence. But there's a nice effect that cancels it, which is the fact that if you have like gluon, you can have also gluon and anti-gluon, and these two diagrams cancel. And the same happens with QED. So you can have particle-particle or particle-antiparticle, which changes a single sign, and then this potential singularity is not present. Okay, which matches, of course, with the known two-loop thermal partition function, which is finite, some R number that is well known. Okay, which is this one plus the one in the previous page. Okay. Now, all right. So let me make some comments about what do we know of the thermal or the question of a state of QCD. Okay, what do we know as of today? Because I think we would try to improve. I think so. I think this could be a program using this equation and our much more knowledge of the S matrix to improve our knowledge on the equation of the state of QCD. Okay. So what I showed you in the previous slides was this calculation and this calculation. Okay. Now let me tell you what else do we know. Okay. As of today. So at 3 loops, famously, you have already IR divergences, but these IR divergences are quite benign or easy to treat, so you can do some simple power counting in terms of powers of energy, propagators and loops, and well, you'll see that this diagram is IR divergent. Okay. Now the standard way of curing this IR divergence is via the divide mass. So because gluons in a thermal background, they acquire a mass. And well, you can easily show that. So the divide mass is of this order, G squared, T squared. So we put the divide mass on these 2 blocks. You'll see that now this diagram, well, it's finite. Okay. And I think divide mass, it generates this fractional power. So alpha x to the 3, it populates. So this is G0, G squared, and G4. So it populates G and G cubed into the divide mass. Okay. And it solves this problem. And the reason why we can solve this problem is so this is quadratic phenomena due to modes of momenta which are of order the GT. Okay. Now this mode, if you compute the expectation value of your potential gauge fields, due to these modes, you'll see that that these modes are not strongly coupled. So you can still resum them and get some final results. This is the topic of hard thermal loop effective field theory, which is, to make more precise, this line here, okay, and to go to higher orders. But the problem arises. There is a fundamental problem or a fundamental limitation when we go to the next order. When we go to the next order, we find yet further IR divergences. They are known as these are a well-known problem. It was pointed by Linde in the 80s. And the issue is that these kind of diagrams, they suffer from an IR divergence that is not cured by the divide mass. Okay? It's a non-perturbative IR divergence. And this is because this is due to modes that are of the order of G squared, so 1/4 power of G times T. Okay? So there are a number of ways to see that these modes are strongly coupled. Okay? One simple way is that this so you can estimate what is the overall coupling that controls vacuum thermal loops. Okay, and they are controlled by G squared T, okay, some factor of pi that you can put on the loops, and some mass scale, which enters in the propagators. So in the case of the divide mass, you see if so this parameter can still be perturbative if you have a mass that scales as GT, because then the perturbative expansion will be G over pi. So if you put G small, you are back in perturbation theory. But explicit calculation of the 2-point function of the gluons shows that only the electric component gets this divide mass, okay, not the magnetic component. So, so this informs us that those components of the gauge fields do not get a mass. At most, you can get a mass 1 power down, G squared T, at most, those modes. So G squared T, if you plug it here, you get 1, which means no way you can restore perturbation theory, even you go to very small coupling, okay? And another way of seeing, well, an explicit way of seeing this divergence is simply that you can, by power count, you can write this diagram as such. So there are some number of loops, number of vertices, a number of propagators. I put some IR cutoff. And so for these very soft modes, it's only the zero mode that matters. Okay, so you can forget about the sum over the KK corrections. And you see, if we plug here 4 for 4 loops, we get these low divergence.
So because of non-perturbative nature, the canonical way that is solved in textbooks is that you should, because it has to do with these zero modes that are strongly coupled, you can simply look at three-dimensional QCD. And this theory develops a mass gap. And well, there are even some lattice calculations for pure Young mills. And you can compute these parameters and match the partition function of three-dimensional QCD with this dimensional reduction of the 40 the thermal circuit. Now, I don't have much more. So this is a review of what is known. I should say that this is not known in a full body. It's just known in some. It's not known in the full QCD with all the matter and so on. Now the hope is that that perhaps we can do better, or alternatively, by treating better by tracing correctly over the perturbative S matrix. So perhaps we can use the S matrix in a more inclusive way. That instead of that we can we could use a more collider approach to relate these genuine non-perturbative effects not to lattice calculation but to a hadronization scale or a different way of treating it that perhaps we can do further progress. That's the dream. Okay. Now. Any question on here? Yeah. Yeah, there are UV divergences, but those it's fine. Yes, no, it's not different than those are short distance, so it's not different than the usual ones. Okay.
I'm still a little confused how you got the mass scale, because like all the perturbative diagrams you wrote down were like there's no scale whatsoever. Like they're all just massive gluons, nothing else. So there's inherently in this diagram.
Here?
Yeah. How do you get the dimensional scale from?
I don't know.
Like,
well,
anything that's dimensionless.
No, yes, sure. This was a bit quick. So this is yeah, I'm already doing a resummation of the two-point function of gluons to write this equation. So here using the fact that if instead of the vacuum diagram you compute the two-point function, okay, of gluons, you will see that it's proportional as temperatures to G squared T squared. Okay, and then standard this in the off-shell treatment of this calculation, what is typically done is that then you just resum this two-point function, and then this cures this IR divergence.
It's not the vacuum.
No, not the vacuum, the two-point function. But this cures only the IR divergence to modes that are this soft, but not the ultra. These are called, I think, soft modes, and these are called ultra soft or something. There is the naming in the literature. Yes.
I try to understand the result depends on these infrared divergences, like the thing that you're computing. I guess the equation is that these corrections, what you're computing, will be infrared divergent.
No, well, so it's a good question. I believe that so the observer we're computing is not infrared divergent. That's what we're computing. But the intermediate steps are. So the question is, how do we get around this problem? So yeah, the observer is well defined, and there are perturbative IR divergences and non-perturbative IR divergence. The perturbative ones can be computed in an effective field theory manner, where you decompose your theory in the various hard and soft modes. And then there are these other modes that are genuinely strongly coupled, and those there's no diagram that will solve it. Okay.
In the collider setting, would this be the Parton distribution functions kind of thing, where you have to absorb some IR divergences into some perturbative structures?
Yes, that's the naive hope. But these are underdeveloped. These I look feedback from amplitude people from collider fields how to do. Yeah. All right, so this is the status of QCD, but what we know from the usual textbook calculation, but because this formula I presented at the beginning is somewhat mysterious and has only been used, has been mostly used in non-relativistic systems. What I wanted to do first is to test it to very large orders in a simple problem than QCD, okay? And what I would like is a model where I know the S matrix, I know the partition function, so these are all the requirements I would like. So I know both sides of the equation explicitly. I would like that there are no physical error divergences, so that if I encounter error divergences in my calculation, I should just keep working harder and eventually they will cancel. And well, and the last comment is if the model is interesting by itself, even better, okay? And there is a model that satisfies all these three requirements. And this is the theory of the scattering of the so-called Brannons in the flux tube. Okay, so here you consider a two-dimensional system. Okay, and basically you scatter Goldstones in this two-dimensional system. The only peculiarity is that this is a target symmetry that is the non-linearly realized target point carrier. Okay. So we are scattering Goldstones in a line, basically. Very simple model. And well, these studies have an interest by itself for people that are interested in understanding the long string sector of a confining theory. This is a very interesting role there. So what do we know here? So these are nothing but Goldstones, but the interesting thing is that if you insist on the target non-linear realized point carrier symmetry, then you can solve the theory exactly. And by solving exactly what I mean is that we know the exact N2N S matrix, like scalars flowing to the left and scalars flowing to the right, and they can interact at some points. And so this is like a space-time diagram. And when they interact, they get a phase given by the Mandelstam variable that you construct out of these two lines. So it's just super simple as matrix, okay? And now this matrix is going to be the correct one due to a number of crosses that have been done. One of those is that it reproduces the correct partition function that you expect from Lycon strings, from Lycon quantization, okay? And this is the vacuum energy of a longer string, and what I want to say is that, well, so on the original equation I showed today, this will be the right-hand side, and this will be the left-hand side, the free energy, okay, of what we are computing. So now we can expand this free energy, and we know what should we be getting at each power on in LS, okay? Yeah.
You're assuming that there's no corrections to number.
No, I'm not assuming this. What I'm assuming, what I'm assuming is that I have a two-dimensional theory that realizes the nonlinear point carrier. The look it takes the action. This is a bit of a scheme dependent in the sense that if you want to realize this matrix, you will need to add. So let's say you want to realize this matrix by using Nambu-Goto and BIM-REC, you will need to keep adding a higher curvature invariant in your worldsheet. But that's fine. Let's say it's not an invariant statement to say which operators enter. So what is invariant, what is more invariant is that these are the S matrices, which are the symmetries of the problem. And the symmetry of the problem is that it realizes non-linearly.
Would you expect correction for this too?
Yes. So the question is whether this system can be realized in nature or so. So in principle, any quantum system that gives a very long flux tube, a sector which has a very long flux tube of pure glue or whatever, it's going to have this worksheet description, and you will expect that most of those systems get corrections to this. Okay. So these are an integrable realization of the flux tube, if you wish, which has a nice thing that we know the exact partition function. Okay. Now then. We're going to talk more later, but this is a bit off topic of it all. But we don't know about any bulk theory that generates an interval flux. This is not known. So even like simple candidates like QCD are now well established that there are corrections to this equation, even in large QCD. But to me, this is a toy model where I have a system where I know both sides. Okay. And I also know the action. Like we can write a very simple action that allows me to compute perturbatively either this or this. But we're not going to use the action, but we are going to use this DMB formula, this Dashen-Man bars. And related to your question, one reason why it's interesting this DMB equation in this context is that this connection between S matrix and the partition function for this theory has been done to the so-called TVA, the thermodynamic Bethe-Ansatz, which is a method that only works for the case where the S matrix is a pure phase. Okay, but actual measurements in the lattice show deviations from this equation. So how are you going to connect, say, lattice with S matrix? So the DMB could be an answer to this question, where you could connect the interval breaking with calculations here. So that's another motivation for using this system. Okay, so the last part of the talk, what I want to show is just to make a few comments on how the DMB works in this system. But first of all, there's a nice thing, which is there's an apparent paradox even before starting the calculation, which is that this is a pure phase. So if I take the log, I only get LS square corrections. But here on the right-hand side, I have LS to arbitrary power when I expand. Okay, so this already seems to be something fishy going on, and these are occupied most of my thinking at the beginning of the project because we have this Dashen-Man formula, but when I plug the simplest system I know on Earth, it's giving me a contradiction right on the spot. So what is the solution of this apparent contradiction? Is that there are two limits that do not commute here, which is the epsilon going to 0, the complete off-shell limit, the complete on-shell limit, and the forward limit, the trace. Okay? So what you're supposed to do is to be on the support of the trace first, and then epsilon going to 0. Okay? And this is going magically to give up, it's going to modify this formula because it's going to require some epsilon here, and it's going to produce all these higher order corrections that are missed if you're not careful with these two limits. Okay? So that's the solution. So here I would not like to bother you with all the calculations of the paper. In the paper, we went up to this order. Okay, here. Let me just make a few comments on this calculation on this order and how this order of the limits shows up. Okay, and with this and the intricate calculations are in the paper. So, for instance, this is the 3-2-3. This is the space-time diagram, if you wish, and this is the exact result. And there are these two possible delta functions. And so there are a number of Riemann diagrams that give rise to this expression. And not all of them are singular in the forward limit. But the one I'm putting here, it is singular. Okay? Because Q squared can go to 0. Okay, so the simple small technical thing that one needs to do is that you can convert like this Feynman-like expression into old-fashioned perturbation theory via identities of this type and generalizations thereof, and then you can when you plug in these decompositions of of covariant propagators into this old fashion where you can distinguish going forward and backward. Then at the same time, you need to resolve the propagators. So the propagators are on the support of the trace, which I'm mimicking here by this delta function. And here it becomes clear in this. So this is an example of these two limits. So this is the real part of this distribution on the support of this delta function gives rise to the derivative of the delta function instead of taking right away the epsilon going to zero limit. Okay. Before considering that you are on the support of that. Okay. So this well, if you did okay, if you take into account this simple observation, you just add up everything and you land into the correct. This is an important mistake here. You land upon the LS4 correction. Okay, not LS square. So LS4 correction. And then okay, using this basic mechanism of computation of the limits, we can reproduce all the orders up to where we had the strength to go. Okay, and so this it's all what I wanted to say. I reintroduced this formalism that was somehow not widely known nowadays, and there well. In fact, in the literature, to my knowledge, there was no literature, no paper I know, and I think we look at thorough search where use the formula to compute 3 to 3, because in 3 to 3 they were encountering IR divergences and they were well, we not made much progress, and that's why I think it was important to go to a problem where we know there were no IR divergences and I insist on the calculation. Now we went even to 4 to 4 and so on. And for outlook, well, one could compute other observables in principle. So one can think of visualization of this equation where I don't know, you turn on some sources, and you can compute some thermal mass, for instance, and that formula will look something like this, where you do create a trace of S matrix convoluted with some form factors of that operator. These have not been much explored. It could be interesting, and most important, I think, it could be interesting to revisit the perturbative QCD equation of a state with this formalism by going to the next order, which we haven't yet. So, okay, that's all. Thank you. Yeah.
Instead of going to this 2D flux tube model,
yeah.
So can you compute the same thing in N equals 4 superior MLs in 4D? Like instead of QCD. So like what? Because then like we couldn't get let's say in the planar node.
Yes. What do you know? The partition function? I did some small search, but I'm not sure I got everything. Huh?
And the planar node, you know it.
By everything, you mean you also know the partition function?
The function of the coupling.
I don't know, as a function of the RA.
You don't know the answer. Yeah. You don't know that. You know that it's wrong. You know what weak coupling and strong coupling.
Okay.
Not known at all values of the coupling.
But even if let's say either a weak coupling or a strong coupling. So a weak coupling, like, you still get this Linde problem. Like sorry, like I think this Linde problem is
You don't get it there.
in QCD it's there from the confinement, I guess, like somehow.
Yeah.
So like how did you say I just want to know like how to see diagrammatically N equals 4, like stuff will all be fine. A priori it's theoretical.
Yeah.
Symmetry cures you that you don't get this.
Conformal symmetry is probably not. Get an exact T to the 4 of it.
Yeah. But I mean, something is broken, like if you're on the back.
Only one thing, the only thing based on almost energy is the temperature.
Yeah.
And nothing else. So the free energy is exactly P to the fourth with the constant, with a T independent constant. That you can compute.
Yeah,
That's it.
but the constant in front is known as a function of the coupling to some order, I guess.
If we coupling, it's known to some order, and then it's known as interstrong coupling.
Mhm.
But not all the values. I don't know to what order it's known in weak.
Maybe like 2 orders. Yeah, 2 orders. But I mean, is your formula supposed to be valid or non-perturbably with some interpretation of what that SAE means? If it's a non-trivial fixed point. SAE means something.
I don't know the fixed point, you mean? The question,
Well, like,
what does it mean?
before you know,
Yeah,
you get a non-trivial fixed point, so then we the meaning of the S matrix.
I'm not able to comment on what does it mean at the fixed point, this formula. I know there's been works where they try to define an S matrix type, an S matrix for CFTs. But I don't know if that would be the S matrix that you would be plugging in this equation and have some consistent.
But if you can ask a similar question in QCD, it's a kind of a question with infrared divergences.
Mhm.
Already it's. The question of whether the trace you're taking is sufficiently inclusive to somehow canceling the infrared divergences you reckon.
Yeah, I think to the extent, to the extent that the original part of the derivation makes sense for QCD, the trace over the Hamilton and so on, which I think it does. I think the issue then is how you feel your asymptotic states when tracing over the S matrix. So.
Right, in QCD, eventually it's sufficiently high order, you get punished for using the wrong asymptotic state.
Right. Exactly.
And the same thing will happen here. The question is whether you will be able to sum.
Yeah, I agree. This is the main question on how you use it at higher orders. I don't know the answer to that. Something I like to understand better.
Those are your connected trace thing, that was sort of inherently perturbative.
No, the connect. I don't think the connected. Why do you think it's perturbative? The connectedness is a statement about extensivity, no?
Okay.
So it's not really something perturbative, I think.
So I would hand you some formula for the SAE.
No perturbative.
I got it, you would have.
Yes. Yeah, then in principle, you could use it here. So related to your question, of how do you use it if I have a God-given equation for the S matrix, this would be like an example. No? You give me the S matrix God-given and you compute it. And I should confess that even here, we don't claim complete victory in the following sense, which is that the relation is given by the TVA equation, which is a nonlinear differential equation, nonlinear integral equation that has a kernel that involves this phase and from which you can derive but we didn't manage to derive TVA from this equation. You would expect you should be able, if your S matrix factorizes, that somehow you can manipulate that trace and reduce it to the two particle sector only, and it should look exactly like TVA. It wouldn't match. So it would be the simplest thing to try, because then that you could use it for you would use it with non-perturbative S matrix and to deal with this. So the linear results, if you wish, is some understanding about how the forward error derivative is cancelled. Is the really small step. The rest is more of a revision and testing. Yeah.
This the big conference for this related forward, the missing subroutine in this model.
Yeah.
Why do you know such problem for QCD?
Why there is this problem in QCD?
The problem doesn't seem to be there in QCD.
No, I think it's going to be, yeah, it's going to be even worse in QCD because in QCD you're going to have naive IR divergences that cancel and true IR divergences that are carried by collective modes as the. So these are, yeah. Which is a problem where the IR divergences are fake in this problem. Like QCD are going to be fake and true ones, let's say, in physical words. It's a funny question. Have a look at the question.
But do you have any idea in what these Linde like singularities are supposed to get absorbed? Like when you do that? I mean, there must be some sort of description how you compute this whole thing, get some, and add some other structure, non-perturbable structure constant somehow, and get a finite result. But where else is supposed to go? Is like the effective couplings of these things? So
I mean, where did it go in terms of an effective filter understanding? Or how you can use it? I mean, it goes directly to the identity operator, to the partition function calculation. There's a contribution there that receives a correction. So the question is, how can you use it to go to higher orders or?
yeah, I mean, same sense like in cross-section calculations, I know that certain AR divergences like in fact like put into like a part of the definition of part of what's the analog of that in this interpretation?
What it's more conventional. I thought you just shouldn't integrate over the zero mode, right?
Yeah.
We're just doing effect, and we're just integrating.
Like, you can't just like throw out the zero.
But don't throw it out, keep it, don't integrate over it. Freeze it. We're just doing effective field theory, and you integrate out all the non-zero modes, you keep the zero mode frozen. For later. Just standard. Low energy effective.
Yeah. Only that only that the zero modes of interactions are not controlled by a small parameter. So
Exactly. But in practice, nobody does calculations this way because it's hard to do loop calculations this way. But if you could just keep the zero mode as an arbitrary function and you could integrate over all the non-zero modes. And you have a completely weakly coupled effective Lagrangian with the zero mode, which would look like 3D QCD plus correction.
Yeah.
And you could solve that on the lattice or whatever.
Yeah. But this is how it's done.
Right.
Yeah.
Look for something else. Than that.
No, I think that's.
Not a stack of speakers.
Okay, thank you.